All right, welcome back. Mech 1330 Fluid Power. We're getting into Chapter 8, Hydraulic Flow Control. All right, so what do we really want to do? We want to control the flow, and we call that metering. So we're going to do two different types here. We are going to meter in, or we're going to meter out, okay? So when we're metering in, we're controlling how much flow is going into the cylinder, whether we're extending or retracting. Okay, we're trying to control how much fluid's going in to either make it extend or to make it retract. Okay, so that's metering in. The most common method is metering out. We want to control how fast fluid is coming out of the cylinder, whether we're extending or retracting. Okay, we want to control how fast, all right, so we can control that speed while it's doing work. Okay, and what do those look like on the inside? Symbol, as you know, you need to write down that symbol, okay? And the line through it means, you know, that we're doing the flow control, all right? Remember, that line through anything generally means it's a variable type control, and this is a variable control for us because we can turn the screw, all right, and it changes how much flow we allow through the system. Okay, so we use what we call a needle valve. So that's what the symbol here is. It's a flow control needle valve, okay, and we're turning that manually. It's an adjustable orifice that can be closed to reduce the flow rate, okay, or we call them metering valves. And remember, orifice is just a fancy name for a hole, okay? But we also use them as a manual shutoff valve. We have a lot of this on the 870 trainer, okay? Each double-acting cylinder we have a needle valve on each end of it. So I can control how fast it extends or retracts, or if I'm making it hard for you to troubleshoot, I completely close off the flow control using that. Okay, but when we do these, we can only control the flow in one direction with these specific valves. Okay, so we either control flow in or control flow out. So remembering, metering out is the most common method of control. Okay, we also have the pressure compensated valves. We've talked about these before, but they automatically adjust the size of the orifice in response to changes in the pressure of the system. Okay, so we use a spring-loaded compensation spool that reduces the orifice size when upstream pressure increases. Remember, this is the one where we're monitoring not its own stuff, but monitoring the main line. So you can kind of take a look at what that looks like here, you know, schematically. So what's really the difference here? Okay, it's still got a needle valve in it, but it also has a check valve in it as well. Okay, so we force everything over the component. All right, so the flow coefficient, it describes the relationship between the pressure drop and the flow rate. So it's given by this equation here. Q equals CV times the square root of delta P over SG. Okay, where CV is our flow coefficient. Okay, and we can see what the units are, whether it's imperial or metric. Delta Q, that's the change in pressure, or the pressure drop in this case. Q is still our flow rate, and SG is our specific gravity. So let's do an example here. We have a valve, the flow coefficient of 2.1 gallons per square root of PSI, has a pressure drop of 35 PSI. What must the flow rate be through the valve? Okay, using standard hydraulic oil, that specific gravity is 0.9. All right, so we have everything we need to calculate Q. All right, so Q from before is CV times the square root of delta P over SG. Literally, we substitute everything in, okay, because it's asking for the flow rate, so we end up with 13.09 gallons per minute. Okay, same example here, type scenario, but we have a valve with a flow coefficient of 2.2 GPM per square root of PSI, has a flow rate of 20 gallons per minute. What must be the pressure drop? And standard oil is used. So our specific gravity is 0.9. So now we have to solve that original equation for delta P. All right, and I'll work that math out on the board for you if you get stuck. But we take that original equation of CV times the square root of delta P, okay, over SG. We have to divide by CV, and then we have to square both sides, okay? And that'll help us get there. But I'll work through that one on the board. But once we get the equation correct, it ends up being Q squared divided by CV squared times specific gravity. Substitute in our given values, okay? and we've found that our change in pressure, all right, is 74 psi. So this is an equation we can use the flow coefficient to either find our flow or our delta P, or we can also find CV when we're looking for these. And in general, if we have a larger CV, it's a smaller pressure drop at a given flow rate. Okay, let's talk about metering again. All right, a cylinder has a 3-inch diameter bore and a 2-inch diameter rod. The pressure relief valve is set to 3,000 psi. If the meter out flow control valve is closed completely, what will the pressure be in the rod end? Assume the piston diameter is the same as the bore diameter. Okay, so once again, we're used to doing these. It's pi d squared over 4, calculating the area. You should know how to do that by now. And we want to calculate the blind end force. All right, so that's the pressure times the area of the piston. So our blind end force is 21,180. Not a new equation, guys. Still the same equation that we were using in Chapter 2. Okay, calculate the pressure in the rod here. Okay, so that's going to be force divided by the change in area. Once again, still nothing new that we've done there. We're going to take that 21,180 divided by the change in area, because that's the pressure on the rod side. Okay. Now, pressure intensification. Happens in cylinders if the flow control valve is completely closed, right? If we don't allow any flow, there's going to be pressure that builds up in that line. The cylinder won't move and the pressure builds up. Now, that's a disadvantage of metering out in that case if we completely close it. Now, one other thing, that you want to think about in that, and this applies to your labs, right? When that pressure is already built up in the line, remember that it's harder for you to use those quick connect cables to put them on and off, because you have to beat the pressure in the line and pop it on at the same time. So we have a couple different kinds of loads here. We have a tractive load. That's a load that acts in the direction of movement. That's when we're going to meter out. We have a resistive load that opposes the direction of motion. That's when we meter in. Okay. We also have a bleed off. That's an additional line. It's run through the flow control back to the tank. Now pneumatics bleeds obviously to the air. All right, but we use a bleed off to slow down the actuator, and some of the fluid is bled off through that line. Okay. Another way we want to be able to, slow down cylinders. We want the longevity to last, because if we're using something that's going to be extending and retracting, multiple times a minute or something like that, we want to make sure that we, do the best we can to preserve our equipment and take care of it. So we can use what we call cushion cylinders. So we slow down the cylinder before it reaches the end of its stroke, all right, so that there's not a hard thrust against the inside of the bore on both sides. Okay, it helps prevent a clamp from doing damage to itself or a workpiece. Okay, we can also use flow dividers, so we can divide the flow from a pump into 2 or more streams of equal flow rates. All right, when we do something like that, we talked about those in the last chapter as well. Okay, and then some different things that you're going to look for when you want to buy a flow control valve. Okay, or you need to repair one or install one. You're always going to want to look at the data sheet from the vendor. All right, but what you're really looking for is, what's the max pressure, what's the max flow rate, what's the filtration level, what's the fluid type, what's the size, what's the mounting, what's the porting. If it's an existing system, you have to make sure that whatever valve you're buying, okay, matches exactly what's already happening in the system. Your system, you could be working on something 20 to 30 years old, but you still want to make sure that all the other aspects, especially like pressure and flow and those sort of things, are all matching up to the original working system type piece. But all right, guys, well, that's it for flow control, and that's it for all of our lectures on hydraulics. Okay, next we're going to step into pneumatics and start getting on that aspect of everything, and everything's going to be almost relatively the same calculation wise. Now pneumatics, we're going to start talking about different atmospheric pressures and those sort of things, but pressure is still force over area. That part's not going to change. Okay, common theme throughout all the chapters. But email me if you have any questions, else write them down. Ask when you come to lab. So anyhow, that's the end of hydraulics, guys. Have a great day. I'll see you in class.